hi there, Nick here, M0NTV, and welcome back to my shack. And hey, long time no see. Sorry about that. Been a couple of months since I've managed to post. Just life and work and everything gets in the way. But I'm back, and yeah, I've not been idle for the past couple of months. Been playing around with a few things. Last time I did a video on AM modulators. I've been playing around with FM modulation and demodulation and had some fun with that. I haven't done any video stuff on that because I'm going to have to return to that, I think, when I know a bit more about it. I need to do a bit more study and understand it, but that's good fun, and some other stuff as well. But you know, I can't stand up to the call of building another SSB transceiver for too long. You just get the itch and you've got a scratch. So what I want to do today is a bit more of a different kind of video, I guess, in that I'm not going to build anything, but I want to talk about what I'm hoping to build and some of the kind of design considerations and things you have to think of if you start wanting to build an SSB transceiver. One thing I can tell you is I've worked out an enclosure and I want to build it in this. Okay, and if this looks a bit familiar, the first transceiver I ever built was Pete Giuliano N6QW's Sudden transceiver that he had published in Sprat, 2 editions of Sprat, and it went in here, and it's on my shelf, and I took it down the other day and it works a treat. Since then, since I've been using my own designs, they've got bigger and bigger, and I've put them in bread bins, and and the last one, of course, was on a wooden shelf. So this is going to be a challenge for me to build something that's small enough to go into here. So yeah, particularly as I'm hoping it's going to be a dual band radio, and because I don't want to just keep building the same radio over and over again, I'm building it for 2 bands that I've never built anything for. 2 of the higher HF bands, 15 meters, which is one of my favourite bands when it's open, and 10 meters, which again can be very exciting. Lots of good DX opportunities there. Recently, when I've been doing any operating, I've been working a lot of QRP and kind of rediscovered my love for QRP and excitement. I've been able to kind of work people with just very little power. And so it's going to be a QRP rig, it's going to be an air, and it's going to be hopefully for 15 and 10 meters. One of the considerations I'm going to use is that I'm going to try, and this will again hopefully help to keep it a bit smaller, but to use the same design for the RF amplifiers as far as possible. Now clearly that's not going to be the case probably for the driver and for the PA, but for the other small signal RF amplifiers, I'm going to try and use the same design. That's the hope. And it's going to be the design that I did a separate video on, the Wes Hayward and Bob Kopsky's termination insensitive amplifier. And because I build that circuit a lot anyway, and because I was calculating I'm going to have to build quite a few fairly identical amplifiers for this project, I took the step that I've only ever done once before, and that is to get on Eagle, the schematic capture and PCB design software. So I've got a free version of Eagle, and designed my own printed circuit board and sent it off to a fab house in China, and produced these, which in cool blue, not even the normal green, so this is the termination insensitive amplifier, and if you put 2 of these together back to back, it's bi-directional, and that's what this rig's going to be. But yeah, nice and small, and actually that's about half the size of when I've built them myself, just Manhattan style or ugly style. So yeah, so I thought that would be good, and I'll do another. I've done this video before, but I'll do another video when it comes to building some of these, and how that kind of works out. Right. Well, without any further ado, let me show you what I hope to do. Okay. Well, here is what I'm thinking at this stage anyway, the new radio is going to look like. And this started life just as literally as a pencil scribble on a piece of paper, but I tidied it up a little bit so you can see kind of what's going on here. So essentially it's rather Bitex-like in its architecture really, so a lot of it's going to be bi-directional. Now I've done this before, and so if we start here with the Arduino, so I'm going to have an Arduino SI5351 as usual, producing the 2 clock outputs, feeding the first mixer and the modulator product detector. And I'm probably going to have a more flash TFT screen this time. I got a bit fed up with 16:2 LCD screens. I've used those so many times, and they're simple and easy and clean, and that's fine. But I just wanted a few more bells and whistles, because this is not going to be an SDR. It's going to be just a standard analog superhet kind of transceiver. But I am going to try and use a bit more of the Arduino's processing power to do a few other tasks as well. Mainly just to, again, cut the analog parts count down, so I can shoehorn it into that little blue enclosure. Now what we've got a crystal filter here. I think that is the same as went into the Shelf 17, I think. Here and here are the IF amps, but these are going to be these Wes Haywood bidirectional termination insensitive amplifiers on either side. But I'm hoping actually to kind of extend this bidirectionality a bit further than just between the mixers. This is the bit that normally gets to be the bit that's bidirectional. But actually, I want to extend the bidirectionality right up until, well, almost to the antenna. These are relays, by the way. So there's a couple of relays which control the signal flow here. These 2 relays are just switching the 15 meter and the 10 meter bandpass filter. But because these are higher RF bands, I'm thinking I'm going to need some RF preamplification. And on transmit, incidentally, the green arrows correspond to receive. So you can see that you can follow the signal path through on receive, through the appropriate bandpass filter, through the RF preamp, through the first mixer, IF amp, crystal filter, IF amp, product detector, and then through the relay to the audio amp. And on transmit, from the microphone through the mic amp, and then into what's now the modulator, through the IF amp, through the crystal filter, through the next set of IF amps, through the transmit mixer now. Then I'd have some small signal transmit amplification. So what I'm going to do is just basically do the same. So so this will be an RF preamp on receive, but it will be a small signal transmit amplifier on transmit. That's the hope anyway. Then it'll go on transmit back through the appropriate bandpass filter, and then we'll hive it off then to beef it up through the driver, the PA, and finally the transmit low pass filter and out. So that's the basic gist of it. So I'm hoping that could be four separate individual amplifiers here. So that's quite a few of them. But if they're all the same design, that's going to be easy for them to kind of stack together, I'm hoping, and use. We shall see. That's the thinking anyway at this stage, and it may change as I go along. What else to say about this? Well, I've put a few little notes here. The first mixer, will be a diode ring. The second one, which is the product detector or the modulator on transmit, will be an identical diode ring plus the W7EL Roy Llewellyn audio diplexer, which is a tiny little circuit. And if you saw the stuff I did with the glue stick permeability tuned oscillators and building a direct conversion receiver, I had a lot of AM breakthrough until I put that W7EL audio diplexer on there, and it absolutely cured it. So that's a winner for me. It's very few extra components, and really does the trick, and make sure that your audio port sees a good 50 ohms termination. So so that will go on there. The bandpass filters will be grateful thanks to Hans Summers of QRP labs, and I build to his designs for those. And what I'm hoping to do with these is to have them automatically switching. So again, this will be something that will be controlled by the Arduino. Yeah, I'm not sure about what I'm going to do for a driver or power amp yet. The AF audio preamp and amp, probably I'll go back to using the 5534 preamp and the LM380 for the power audio amp. And the microphone amp is going to be this little SSM2167 audio compressor breakout board, which I've done a video on before. But I will return to that because I fixed the issue that somebody highlighted to me, which is that the resistors were the wrong way round. But I won't say too much about that now. But I've actually got it working properly and got the compression working now. So it'll be interesting to see that. And then finally, a power distribution board, which is just my own design set of relays. And again, that will be timed and controlled by the Arduino. So that's basically what I'm looking at. Now, how will it work? Well, there's a number of things you have to think about, particularly when you're working to your own design. You know, when you're following somebody else's design, you kind of hope they've sat and thought about this stuff, but when it's down to you, it's not immediately obvious when you first start doing it, and usually you find out somewhere down the track and think, this would have been really helpful if I thought about this before I built all these circuits for this particular frequency. I'll come back to those things down the bottom left in a minute, but let's just start. If this doesn't float your boat, if you just not interested in this, then just fast forward through this bit. But if you are interested in how this works, then, well, pin back your ears. So, okay, here we go. So we've got our first mixer, and let's say we've got a signal coming in, and I'm just going to do this for the 15 metre band, and let's not worry about 10 metres at the minute. And just to keep the maths simple, let's assume that our signal is 3 kilohertz wide. Now I know it's probably not going to be, I mean most of mine are 2.3, 2.4k, but just to keep the maths easy, let's assume it is. And let's assume we've got a signal, and we're on receive here. I'm only going to do this on receive. The transmit is exactly the same, it's just in reverse. But let's assume that we're receiving a signal which is right at the top of the UK allocation of the SSB portion of the 15 metre band. So 347 to 350, and we've got a local oscillator of 34.676 megahertz, and what that will do, as we know, mixers, 3-port devices, 2 inputs, 1 output, but we'll get 2 different outputs on our output port. The sum will be the RF plus the local oscillator. And you'll see there, if we take the extremes of that signal, the 21.347 and the 21.350, and add that to the local oscillator, it gives us a 3 kilohertz signal lying just north of the 6 metre band. We don't need to worry about that. That's miles outside of our area of interest, and that will be filtered out anyway. What we're interested in is the difference. So this is the RF minus the LO. And if you take that same 3 kilohertz signal and you minus the LO from it, you get a signal that goes from minus 13.329 to minus 13.326 megahertz. Minus 13 megahertz? What's that about? Well, of course, there's no such thing as minus 13 megahertz, there's just 13 megahertz, but that minus gives us a very important signal. Let me just illustrate it like this. So, okay, here is our upper sideband signal then. So it's sat there between 21.347 and 21.350. Now, you've probably seen these little diagrams before. The smaller bit on the left-hand side, if we're talking about the vertical height of the signal now, corresponds to the lower audio frequencies of the modulated audio signal. Okay, and so the right-hand side, where there's a higher vertical element to that triangle, corresponds to the higher frequencies of the modulated audio signal. So in other words, it's the right way round, because the higher up in frequency you go, from 21.347 to 21.350, the higher up in the audio frequencies you go. So that's an upper sideband signal. Now, if we look at the IF stage, so remember our IF is 13.3 megahertz, what happens is this. Okay? So we get the signal inverted. And that's what that minus symbol tells us. It means that the waveform is inverted. So that, of course, is a lower sideband signal. That's good. We want it to be, because this is at the bottom left here, a single conversion superhet, which means we're only going to do one RF to RF frequency translation. We're going to translate the frequency twice, in fact, because we're going to take it from the IF down to audio as well. But it's technically a single conversion. But what if there's a signal 3 kilohertz down, another upper sideband signal? So we're trying to listen to the one that's sat between 21347 and 21350. But what if there's a signal 3 kilohertz below it? Well, guess what? That'll be mixed down there as well. So the highest point of that yellow signal is very close to the lowest point, and very close to where the carrier will sit. So it's very important, of course, that we filter that signal, and that's what the crystal filter does. And this is the beauty of the super heterodyne system. So we build a crystal filter, and we just let through the bit we want, right? And maybe not even all of that signal, because we might cut out a few of the lows, we might cut out a few of the highs. And you can adjust that, because you can't adjust the crystal filter easily, but what you can do is you can adjust your oscillator signal to make sure that you can squeeze it up or down, depending on whether you've got too many highs or lows or whatever. And of course that gives us this, which is what we want. The high side injection just means that our local oscillator signal is higher than the RF that we're trying to demodulate, right? So the local oscillator signal is higher. And that's where you get this spectral inversion, it's called, because we're using this high side injection. Now, you don't have to use high side. You can use low side injection. Now, low side injection is, as you might imagine, where your local oscillator signal is lower in frequency than the RF that you want. And you could look at it and say, well, look, the signal's at 21 megahertz. We've got an IF that's set for 13.3. Why don't we just have a local oscillator running at, it's about 8, isn't it? About 8 megahertz, and subtract that. So, to get your 21.347 and minus the 8 from your local oscillator, and that would still get you back to the required IF stage. Well, yes, it would. Right? It would. But what you've got to be careful of is the spectral inversion. So because some frequency translations will give you this spectral inversion, some won't. I'm not going to go into all that now. But also, you've got to think about, if you've got a local oscillator signal that is lower than the frequency that you're interested in, you've got to be concerned about the harmonics of that local oscillator, because the local oscillator is the most powerful signal in your radio. Far more powerful than the faint DX station you're trying to tune into. Okay, it's not going to be more powerful than what's coming out of your PA, but in terms of the rest of the radio, though, it's a strong signal. And what you don't really want is that local oscillator too close to the frequency of interest. And of course, the third harmonic, if you were to do low side injection here, it's about 23 point something megahertz, just beneath the 12 meter band. And actually, that's not all that far, really, from your 21 megahertz. So it means that you better build a pretty good bandpass filter, because you really don't want a very strong local oscillator signal so close to where your frequency is that you want to listen to. So there's all these things you've got to think about. So now you might think, well, we'll pick a different IF frequency. Well, you can, but I guess very often the IF frequency is where we start, because it depends on what crystal filters you can get. Can you get them? They're almost impossible to get these days. You've pretty much got to build your own. You can buy a kit, and build one, or you can get your own crystals as I do and build my own. It just depends which crystals you can get and whatever, you know. So that will be the determining thing, really. So you start really with what the IF is, because you don't really have a lot of choice in that, and then you make those other calculations about what your local oscillator is going to be around that. And I just work these things out because it helps me to visualize what's going on. But let's just finish the process. So we've got our signal there, which is now filtered, but is a lower sideband signal at the IF stage. So then we feed it through the product detector. So that's it, 13326 to 13329. We put in our BFO-CIO, so beat frequency oscillator, carrier insertion oscillator, whatever you want to call it. The locally produced signal that we're going to use to mix it down to baseband. And again, we'll get the sum and the difference. So the sum is just below the CB band, I think, really, but again, we'll filter that out, so we don't need to worry about that. And the difference is what we're interested in. And you'll see again, we've got a -3 kilohertz. So here's what we had, our filtered signal. Here's the audio stage, and this is clever, because this is what actually happens here, because we get, technically, mathematically, we get that. We get a signal line between 0 and -3 kilohertz, but it doesn't exist in the real world. So what happens, and what that minus tells us, is the signal is inverted. And what actually happens is that signal folds around the DC point, is what we say. So it does this. Get a load of this then. 3, 2, 1. It goes round there like that. And as it folds around, it inverts, which gives us then a properly orientated audio signal. An audio signal not inverted, so you can listen to it and it doesn't sound like Donald Duck. So that's how it works, and I hope that was of some interest. Well, hope that wasn't too technical. Next time it's going to be more practical, and the following videos now, because I'm going to be building this radio and all those different modules and things, and taking you through the highs and lows, I'm sure, of doing it. I'm trying to fit it in here. That's going to be the real interesting thing. But thanks ever so much for watching, and catch you again soon. Thank you. Bye bye.